First, let's look at what ballast operations are and their purpose. Since a ship's draft is shallow while in ballast condition, it's susceptible to wind and wave impact. As a result, rolling increases and hull stability deteriorates. To improve hull stability, a ship's ballast tanks are filled with seawater. When loading a ship with cargo, seawater in ballast tanks is discharged. Such seawater filling and discharging are called ballast operations, which are conducted either by gravity or ballast pumps. Please note that improper handling of pumps and/or valves may result in various accidents. Shown here is a pipeline laid on the ship's bottom, through which seawater flows for ballast filling or discharging. Joints that connect the pipes are called dressers. There are cases where dressers are damaged. This is an example of a water leakage accident due to dresser breakage caused by abrupt valve operation. Valves are provided where the pipeline is connected to ballast tanks. The pipeline is fitted with many such valves. Improper valve opening or closing can cause accidents. This is an example of an accident caused by valve rupture. In this accident, corrosion in the valve body, combined with sudden pressure change due to pump stopping, ruptured the valve body during a stroke to produce a hole in it. To prevent such accidents, you must have a good understanding of the procedures for proper handling of pumps and valves. Water pressure is a vital factor affecting ballast operations. Water pressure is expressed by the term water head pressure. Let's consider a 10-meter tall water column. As 1 cubic centimeter of pure water weighs 1 gram, a 10-meter tall water column with a basal plane of 1 square centimeter is equivalent to 1,000 grams, or 1 kilogram. Therefore, the water pressure placed on the basal plane is 1 kilogram per square centimeter. This pressure is referred to as 10-meter water pressure head. In other words, water pressure head means pressure translated from the height of a water column. When the water level inside the ballast tank is higher than that of the level of the seawater outside, ballast water can be discharged by gravity, thanks to the water pressure head inside the tank. Discharging by gravity stops when water pressure head becomes zero, as the tank's water level comes down to the same level as the seawater outside. To continue to discharge further from this state of balance, it's necessary to use a pump, pushing the water out with a pressure higher than that of the sea surface. Cargo is loaded under this condition. As cargo is unloaded and the water level inside the ballast tank becomes lower than the sea surface, ballast water is gravity filled into the tank thanks to water pressure head of the seawater. Ballast filling stops when the water pressure head becomes zero, as the ballast water level rises to become equal to that of the sea surface. To continue to fill ballast water further from this state of balance, it's necessary to pump water in with a water pressure head higher than that inside the tank. There are various pump types. Of these, centrifugal pumps are commonly used in ship ballast operations. With centrifugal pumps, a motor is used to rotate a vane wheel called an impeller. The centrifugal force thus generated is used to send water out. Let's have a look at this principle. Put some water in a cylindrical container and turn it around the container's axis as the center of rotation. A centrifugal force works on the water and pushes it toward the container wall, making the water surface form a parabolic arch. As the rotation speed is increased, the centrifugal force becomes stronger to such an extent that the water goes over the container's brim and spills out. If the overflow is collected at this time, and at the same time, a space is created in the bottom of the container through which to send in water continually, the water rises from the bottom to the top of the container. This explains the principle of the centrifugal pump. With actual pumps, when the impeller is rotated at a high speed in a casing filled with water, pressure at the impeller's center area drops. Then, pushed by the atmospheric pressure, the water is allowed to flow into the pump through a suction pipe. The water, which has been splashed by the impeller's centrifugal force, gathers in the volute casing and gains in pressure before flowing out of the delivery pipe. The height to which a pump sucks up water is called pump head. The height from the pump's base plane to the water suction level is called suction head, while the height from the pump's base plane to the water discharge level is called discharge head. And the total of both heads is called total pump head. Total pump head means the height to which the pump actually transfers water from a low water level to a high level. A pump's performance capability can be expressed in terms of relation between total pump head H and discharge amount Q. As shown in this graph, the points where the total pump head and the discharge amount cross form a curve peculiar to each pump. When the total pump head is high, the discharge amount becomes small because a greater pressure head is required. As the total pump head comes down, the required pressure head decreases and the discharge amount increases. Pump output refers to an amount of work with which a pump pushes up a certain discharge amount of water to a certain pump head. The relation between the pump output P and discharge amount Q also shows the pump's performance capability. Cavitation is one of several phenomena you should avoid when operating cargo pumps. When water flows fast through a region, the pressure falls below the water's vapor pressure, causing vapor bubbles to form. As they collect, these vapor bubbles create a cavity, a phenomenon known as cavitation. When these bubbles break, they produce minute vibrations that cause abrasion. Repetition of such vibrations leads to damage to parts of the pump. Water boils at 100 degrees Celsius under 1 atmosphere, or 0.1 megapascals. But on top of Mount Fuji, the atmospheric pressure drops to 0.06 megapascals, causing water to boil at 87 degrees Celsius. As a result, the critical pressure at which a liquid begins to boil under a certain temperature is called saturation vapor pressure for that temperature. The lower the saturation vapor pressure, the lower the boiling point. In other words, vapor bubbles and cavitation occur where water pressure is low. Here's an example of cavitation. It occurs in the periphery of the bell mouth during discharge from the ballast tank. In the event the suction speed increases as the water level drops, cavitation is prone to occur in the periphery of the bell mouth. When it comes to pumps, cavitation is liable to occur in areas around the impeller. Bubbles generated can cause abrasion, and vibration can damage the impeller. Typical damage to pumps due to cavitation includes